Section 5.6, example 25, kind of goes full circle for us now. So using the convergence test. So they just want us to see what tests we would use and testing to see if we converge or diverge. So let's take a look at this very first one. So looking at this, we have numerator, denominator. As we go further and further, we know that, as we go further and further, we know that this, like the parts of this graph that take over are going to be these right here. So let's use that. So we're going to compare this to n squared over n cubed, which ends up just being 1 over n. So let's do the limit comparison test, or just comparison test. So comparison test. So we're going to take the limit as n approaches infinity of a sub n divided by the next one. So a or b sub n. So we're looking at n squared plus 2n over n cubed plus 3n squared plus 1. We're dividing all of that by 1 over n. And let's see. So let's multiply both top and bottom by n. So that's going to give us a limit as n approaches infinity of n cubed plus 2n squared over n cubed plus 3n squared plus 1. Let's see, and then we could divide both top and bottom by n. So the limit as n approaches, and I'm not n cubed. So dividing both top and bottom by n cubed, we have 1 plus 2 over n over 1 plus 3 over n plus 1 over n cubed. So all of these go to 0. So this entire thing goes to 1. So this tells us that either both of them converge or both of them diverge. And so now both converge or both diverge. So now we're going to take the limit of b sub n. So the limit as n approaches infinity of 1 over n. And we've proved this a couple of times already that this one diverges. So because this one diverges, a sub n also diverges. So therefore, a sub n itself diverges. All right, there's that first one. Let's give that second one a try. Now b sub n. This is an alternating series, so let's see what our options are. We could do ratio test. Actually, let's do a ratio test just because we have that n factorial. So ratio test tells us to look for rho, the limit as a, let's move that one. Okay, so ratio test, we're looking at rho equal to, so equal to the limit as n approaches infinity of the absolute value of n plus 1, the n plus 1th term over the nth term. So 3 times n plus 1 over n plus 1 factorial. And we're dividing that by a sub n. So 3n plus 1 over n factorial. I guess we could use we have to throw these in here. So -1 to the n plus 2. Down here, it's going to be -1 to the n plus 1. All right, first off, this being an alternating series, and this here being between negative and positive, we're taking the absolute values. So dropping the absolute values, we could also drop these. So dropping these means we could drop the absolute values. And now let's go. So limit as n approaches infinity of 3n plus 3 plus 1. So 3n plus 4. And that's the numerator there. And we're dividing that by, let's separate this already, n plus 1 times n factorial. And up here we have n factorial. Down here we have 3n plus 1. And factorials divide out. And we're left with the limit as n approaches infinity of 3n plus 4 over here. We're multiplying these two. So 3n squared plus 4n plus 1. And let's see. So as the numerator goes to infinity, the denominator also goes, actually no, the numerator, like if we were to divide all of this by n, the denominator would eventually go to infinity. So this ends up going to 0. And because it goes to 0, this is a absolute convergence, or converging absolutely. A sub n, we have converges absolutely. Perfect. Okay. Next, we're going to have to do this one, these two up here. All right, so we have C. Let's see, what could we do? Let's do the divergence test, just because I don't see anything that like screams out to me just yet. So if it passes the divergence test, then it means it diverges and we don't have to continue on with anything else. So the diverging test tells us to take the limit of this. So the limit as n approaches infinity. So what we're looking for is literally anything but 0. So anything but 0 is going to tell us that it diverges. But if we get 0, then it's inconclusive. So we're taking the limit of e to the power n over n cubed. So this gives us infinity over infinity. So we could do L'Hopital's rule again. So that's going to be the limit as n approaches infinity of the derivative of the numerator, e to the n derivative of the denominator, 3n squared. Apply the limit, we have infinity over infinity again. Let's apply L'Hopital's rule again. But see, as we apply L'Hopital's rule, the denominator ends up like shrinking. So the limit as n approaches infinity of e to the n over 6n, which again is infinity over infinity. L'Hopital's rule again. The limit as n approaches infinity of e to the n over 6. This goes to infinity. And because it goes to infinity, it tells us that this diverges. So therefore, a sub n diverges. Now that we know a little bit more about these, It's a lot easier to just prove that it diverges and move on with the problem than to prove that it converges. All right, let's see what this last one is. This one doesn't look too bad, just because it looks like we could use our root. What is it called? The root test. So the root test tells us to take the limit as n approaches infinity of the nth root of a sub n. So we have 3 over n plus 1 to the power n. I just put it over 1, or within one variable. Okay, so we have that, those two simplify. Oh, and we had like the absolute value of whatever that is. We don't have to worry about that just because the absolute value, like everything here is going to end up being positive. So we would just leave it as this. So now let's continue. So the limit as n approaches infinity of 3 over n plus 1. As n goes to infinity, this whole thing ends up going to 0. But if rho is 0, less than or equal to rho less than 1, then it absolutely converges. So it going to 0 actually helped us. So this tells us that a sub n converges. Not only converges, but converges absolutely. And there we go. If you have any questions, please feel free to ask. Otherwise, bye.